Let us see now how we could solve this complete problem using the D'Alembert method. So the D'Alembert method means that there is a big work that we're not going to do here and that you're supposed to be able to do. This is the one that we did last time in tutorial, and you also used a bit for the lab. You find the correct substitution, and here it's just going to be x. You have a new variable x plus vt and another variable x minus vt. You find the correct substitution that is going to simplify your equation, and so here that would probably be simplified as d2 of your function of the two new variables of the cross derivative is equal to 0, so that you find in the end that it's a sum of two functions. All right. So there is a whole preliminary work that we're not going to address here, but that should be done if ever you have to apply this method. And one question was, should we choose to apply Fourier or D'Alembert? For the exercises we do, you just apply the method that we ask you to apply. Okay, that's just because it's in general, these are some very specific examples of partial differential equations, and in general there is no method that works all the time, so it really depends on what you have. Okay, but here I guess most of them could be described by both methods. All right, so let's assume you've calculated your correct substitution and found that your solution should be written as the sum of two arbitrary functions of x plus vt and x minus vt. That's solving for the equation. And now we're going to see what the boundary and the initial conditions are saying about these f and g functions. Right, so let's do as previously. Let's apply them one by one and see what they imply. Okay, so the first one, u of 0t is equal to 0. Right, so what does it imply for our function? It implies that f of vt plus g of minus vt is equal to 0. That's already a lot. That tells us that f of vt is equal to minus g of vt. So they are both functions of one variable, and actually they are really related to each other in the sense that f of y is g minus g of minus y. Okay, so very simply that tells you that, well, the formula of f is the formula of the opposite of g applied to the opposite of its variable, and vice versa. G of y is minus f of minus y. Okay, so what does that mean? It means that actually my function u of xt will be written, we can use only one function. All right, so let's keep the f x plus vt, and the g is going to be minus, so it's just a minus, f of minus x minus vt, so vt minus x. Okay, so that was for the first boundary condition. Let's see about the second boundary condition. What does it tell us? Tells us that, so second boundary condition is the string is held, so that was held in 0, and we are now held in 1. Okay, so your string held at both ends. U of 1t is equal to 0. Okay, so about that second boundary condition, u of 1t is equal to 0, what does it imply? It implies that f of 1 plus vt is equal to f of vt minus 1, whatever the t. So that just tells me that f of y is equal to f of y plus 2, whatever the y we have. Okay, so what does it imply? It implies that just that f is 2 periodic. So that begins to resemble what we have found earlier, that, well, actually, we had to do an extension of our function defined on 0, 1 in order to make it a period 2 function. Okay, and we could also test for parity, but it's not in the initial conditions. But if we want to try that, we could also try parity. So if I plug f of minus xt, that's just going to be f of minus x plus vt minus f of minus x plus vt, which is minus u of xt. Okay, so we've got two periodic odd function, right, which looks like the thing we had to create in order to use the our function, our Fourier expansion of the phi function. Okay, so fu is odd in x and period t. Next, let's see what is we have to use next. So let's say that our next condition is the initial condition. Let's call that phi of x. Okay, so u of x 0 is equal to phi of x, and this function phi is the triangle function, right? At least on 0, 1, and you know your that, well, what we mean is that maybe we need to periodize it. Okay, extend it and periodize it. So that just means that f of minus x f of x plus minus f of minus x is equal to this phi of x. Okay, so again, and if we use the odd extension stuff, this is what we have. So we have what our f function looks like. Okay, it's we can really obtain that from the phi function. What is our last condition giving us? The last condition tells us that derivative in t at x is equal at t is equal to 0 is equal to 0. So let's see what we have. If I do du over dt xt, that's just going to be, so I'm using the f u of xt is f of x plus vt minus f of vt minus x. What does that give us? That gives us that this is v f prime of x plus vt minus v f prime of vt minus x. Okay, and that should be equal to 0, right? When t is equal to 0. So when t is equal to 0, I get that v f prime of x minus v f prime of minus x is equal to 0. Okay, so f prime of x minus f prime of minus x is equal to 0. And if I use the equation that was f of x minus f of minus x is equal to 0 to phi, sorry, phi of x, and if I differentiate that one, what do I get? I get that f of x plus f prime of x plus f prime of minus x is equal to phi prime of x. So using this equation, no, this one plus this one, I just sum the two equations, I get that 2f prime of x is equal to phi prime of x. So f of x is equal to phi prime of x over 2 plus 2, sorry, to phi of x plus constant. Okay, so what do we get? We get that u of xt is equal to 1/2 phi of x plus vt minus 5 of vt minus x. And as we know that our function phi was extended by odd parity, that's really, so that is really phi of minus x minus vt. Okay, so, and that should be equal to minus my phi of x, so I get 1/2 phi of x plus vt plus phi of x minus vt. Okay, that's what we find. U of xt. This is what we have. And probably if you compute the Fourier series expansion of this function, you will find exactly what we the expansion that we have found in the previous question.